And thanks to the organizers for inviting me. It's really great to have finally a workshop in person again. So yeah, I will talk about our results for the Isovector Axial form factor. And okay, one slide for introduction. Basically, everything on this slide has been said already. So there's again this plot took from this recent review. So as you know, the experimental knowledge on the axial form factor is quite limited, as neutrino-nucleon interactions are difficult to measure. However, they are required as input for neutrino-nucleus cross-sections, which are in turn input for upcoming neutrino experiments. Now, Lattice QCD can be used to compute the axial form factor. And okay, if you're just looking at this plot, I mean, in terms of the errors they're shown here, they're already quite competitive compared to what you could get out from an experiment so far. So Lattice QCD might be able to provide crucial input to these future neutrino experiments. While in the past, people have mostly tried to compute the axial charge and perhaps the radius, which is just the slope of the form factor, or small q square. Now one can also go for a parametrization of the full physical form factors, roughly between 0 and 1 Chef squared. And yeah, it's been already said that now recent calculations for the axial charge are actually in very good agreement with the experiment. However, I mean, the situation is slightly less clear for the Nucleon radius, as is shown in this overview of lattice data from the last 5 years. So there's more variation in here. But if you compare it to what you get out of an experiment, that's still, I mean, the same ballpark and pretty good. So the goal here is really to perform a reliable and precise determination of the physical form factor, which remains a challenging task to do. That's a brief overview of the Mainz Nucleon structure program. So first of all, of course, we're computing isovector nucleon charges and twist 2 matrix elements. This has been published in 2019, but there's also an update ongoing. So I'll talk a little bit about that because GA is kind of a benchmark for all of this. Then we had a paper on the isovector electromagnetic form factors. And of course, then there's the isovector axial form factor, which has not yet been published. I should mention this analysis is actually carried out by another postdoc in Mainz, Jona Kopponen, and previously also by a PhD student, Tobias Schulz. Another thing I'm not going to talk about much today, or not at all actually, is isoscalar contributions that involve quark disconnected diagrams. We have also computed those, so there was a publication on the strange electromagnetic form factor some time ago, and there's also analysis ongoing on electromagnetic form factors. Here there's a disclaimer to make, so the results I show in this talk are all still preliminary, as both of these analyses are still work in progress. Okay, so how we do this on the lattice has also been described before. In principle, you have to compute this kind of ratio of 3 and 2 point functions to cancel unknown overlap factors to get access to the matrix elements you're interested in. So if you talk about the axial form factor, there are basically 2 relevant insertions. So either one in temporal direction or one in a spatial direction of the axial current. Here we will only consider the spatial one in this talk, and then if you plug this into this ratio, you get this expression for the effective form factor. This is what you extract from the 2 and 3 point functions by forming this ratio. Yeah, it's been already said by Sarah in the previous talk. I mean, there's much stronger excited state contamination actually in the temporal component due to these in pi states. And okay, if you want to look at the PCAC relation and so on, I mean, you also need this other insertion. But if you're really only after extracting, I mean, the form factor, then I mean, you can get away with looking at the spatial one, which has much milder excited state contamination. So yeah, we need to compute 2 and 3 point functions. So the 3 point function is shown here. So we have a nucleon produced here and being destroyed over there. We use a technique that has also been mentioned in the previous talks, which is sequential inversion through the sink. And the final state nucleon is produced at rest here. As I said, we'll only consider quark-connected 3 point functions because we are talking about isovector nucleon matrix elements, so there are no disconnected diagrams. As for the technical details, so the renormalization that's required is done non-perturbatively for the axial form factor. And we use the improved axial current for the 3 point function. So the leading lattice artifacts in this calculation are of order A squared, not order A. That's just a technical detail about the calculation, how this is done. So we use something called the truncated solver method. Basically, the idea is to use many low precision solves and use a few expensive exact ones to correct for the bias from that. It gives a huge computational speed up. Now, let me explain, more about these ensembles that we're using. Similarly, as in the previous talk, we use gauge configurations provided by this CLS consortium. They use 2+1 flavors of non-perturbatively improved Wilson Clover fermions. And now in this table, these two numbers here, the number of configuration and the number of measurements on them, these are still target numbers. The production is not entirely complete. This is just to give you some idea of, number of measurements that are being done there. So it's typically of the order of 50 to 100,000, and in some cases less or a bit more. So these ensembles cover 4 values of the lattice spacing. This allows us to do a controlled continuum extrapolation, so between roughly 0.05 and 0.09 Fermi. We have actually many different volumes. Typically, the M/L is larger than 4. This allows us to do the extrapolation to infinite volume and to check for finite size effects. Also cover a vast range of pion masses from even slightly below physical up to 300 MeV. That will allow us to do the Kavli extrapolation and check for its convergence. Finally, I want to highlight these two boxes particularly. So these are two very large and fine boxes, both close to a physical quark mass, one at 130 and one at 170 MeV pion mass. So there's one more thing here that concerns how many of these source sink separations that we do that Andre mentioned in his talk. So we use a fairly large number, as you can see here, up to 14 actually, between roughly 0.3 and 1.5 Fermi. And then we also try to scale our statistics down. So if you go below 1 Fermi, we reduce the statistics by a factor of 2 in steps of roughly 0.2 Fermi. So the idea is to keep that signal-to-noise ratio cosmology, so sink separation is closer to a constant than to see the full exponential increase. Yeah, okay. In some cases, actually, the scaling has been performed all the way up, even beyond 1 Fermi, but that's not so important here. Okay, so now about the axial charge first. So the axial charge can be considered a benchmark observable for lattice QCD calculations, in particular Nucleon structure calculations. That's partly because, the data that you get for GA is statistically the most precise data, apart from electromagnetic form factor data. But there the charge is conserved, so that is not particularly interesting to compute. However, to get a good value for GA, you need very careful treatment of excited states and to really perform a controlled physical extrapolation. So you have to take all the relevant limits, the Kavli continuum, infinite volume extrapolation. And our analysis is now done in a particular way. So we not only use data for GA, but actually we do a simultaneous analysis for 6 matrix elements. So we use the local operators for the axial, scalar, and tensor charge. And then on top of that, we also look at one derivative dimension 4 operators. So this, for example, gives you the average X of the nucleon. Since that is done at 0 momentum, the ratio you have to compute gets a much simpler form, so the square root drops out. And now if you want to extract the ground state from that ratio, and you only have data with source sink separation smaller than 1.5 Fermi, this requires a dedicated analysis. This can be seen in this picture here. Going to larger source sink separations, it's not quite clear that this would have converged at 1.5 Fermi. So to get the correct value, you have to put in more work. Now, there's several options to do that. The most simple one would be just to take the midpoint of the largest source sink separation, but that generally leads to an insufficient suppression of excited states. I can see here, how this residual excited state contamination behaves as a function of pion mass. So maybe you get away doing that with at 4 MeV pion mass, but if you go closer to physical, this actually is a large correction. But that's not being used anymore. And you could try to improve that by doing 2-state fits. So basically, it's the matrix element that you want plus the leading correction. As shown here, typically you do this fits, and you just fit bands and the value up here. This tries to explicitly account for the leading correction. But even with that method, you have a problem issue if you go to very small pion masses, because when you need to leave out some insertion times here on both sides. And okay, what we found in the old analysis, where we had only masses larger than 200 MeV, you could put some criterion like that the number of times lies left out times in pi should be larger than 0.5. But then, unfortunately, if you go to physical quark mass, you find that you have no data points left in that fit, so that's also no good. So what we end up using is the so-called summation method. And there the idea is that instead of trying to fit the dependence on the insertion time, you sum over the insertion time, so there's only one time separation left, which is the source-sink separation. And then you can just do a linear fit that will give you the matrix element that you want. It's kind of seen here. And the advantage of that is that you have a favorable correction from there that now comes with the source-sink separation instead of the insertion time. And also this method can, again, be extended to include higher states. And this is what we do for the charges, actually. So if you consider the two-state truncation for that, you get a more complicated expression, where this MIJ parameters are matrix elements. So again, the M00 is the ground state matrix element. Then the delta is the leading energy gap, and you have these amplitudes, or rather ratio of amplitudes of the two-point function. You can really find these terms to absorb some of the ambiguous terms up here, then you get a somewhat simpler expression. And in principle, this could now be fitted to our lattice data, but if you do that, you still find that some of these terms are not constrained at our present level of statistics, so we do not include them in the final fit model. And in the end, we use tier 2 fit models. One is the standard or plane summation method, and then we use this two-state fits that can be performed simultaneously for all these 6 observables. To mention that, you can also do a slight variation of this fit model where you add this constant C0 here that again receives contributions from all higher states. That's in some sense more similar to the original summation method. That's just an overview of some of the features of the summation method based fits. So one advantage is that if you do these fits, the result essentially only depends on the choice of the minimal source-sink separation that enters this. So there's not much freedom or, for human influence on that. You get away without using any priors in this fits. And as I said, you can fit these observables simultaneously. And then you find that the correlation helps actually to further reduce errors. And also it makes these fits generally more stable than this fits directly to the ratio data, where you have to fit all the data points that you have in insertion time, which has a much larger covariance matrix. And finally, and that's, I guess, the most important feature about the summation method versus a simple two-state fit answer is that it has this favorable leading correction that comes with the minimal source-sink separation instead of the minimal insertion time. Okay, so how does this look in practice? So this is just data on one of our ensembles for the standard linear summation method. So this is the source-sink separation, the minimal source-sink separation, the source-sink separation versus the summed ratio. Then you do a linear fit starting from one point. So in the darker shaded region, this is where the fit actually has support. And now if you look at this closely, going to smaller and smaller source-sink separation, you can see that there's a deviation from linear behavior, and that's exactly the effect of excited states. Now, if you do the two-state fit, you can actually go to much smaller source-sink separations, and the data is described very well. Now, all 6 observables, you can only see 3 in this plot. I show the other 3 in the next slide, are fitted simultaneously, and this fit describes the data actually very well. Yeah, okay, the same thing for the remaining 3 matrix elements, just for the sake of completeness. So this is average X, the Lattice transversity of the Nucleon. Again, you can do either linear fit, then you miss these points, or you do the two-state fit, and again, it describes the data fairly well down to pretty small source-sink separations. However, there's now one thing that you cannot immediately see from the plots. You might think, okay, this describes this all the way down, but that's actually not true. If you were to include this next point, the p-value would drop completely to 0. So that's because the errors are so tiny on these points, even though we scale down the statistics. There you have to be quite careful. You can ask yourself about the efficacy of the let's say, normal summation method versus the two-state method. So results from the two-state methods here are shown in red, and the one from the usual linear summation method are shown in blue. This is just on three ensembles in our finest lattice spacing, starting with 1 at 170 MeV up to 250 MeV. You can see, okay, going to lighter quark mass, the excited state contamination gets somewhat worse. So if you look at the heaviest quark mass, essentially the two-state fit is almost constant, independent of the minimum Source-Sink separation. Generally, you find that the two-state fits allow you to include smaller Source-Sink separations. And okay, in the end, what we do is you have to fix your minimal T-sep that enters the two methods. So if you look at all these plots, you can come up with a criterion to do that. So you allow for somewhat smaller minimal T-seps in the two-state model. But overall, I mean, you can see if you go to large enough minimal T-sep values, this always decrease in the end. Okay, so after we dealt with excited states, you have to still do the physical extrapolation. And for this, we again consider ansatz basically given or inspired by chiral perturbation theory. So this is this fit model shown here. So this is actually inspired by next leading order chiral perturbation theory for GA, plus a term to take care of the lattice spacing and one to take care of the infinite volume extrapolation. Now in this model, A, B, D, E, and F are three fit parameters with, okay, A is just the axial charge and a chiral limit. And this coefficient C is known analytically. So this comes out of chiral perturbation theory. However, okay, this has in principle also been said before. If you were to try just the next leading order fit, including the chiral log, what you find is that this fit model imposes a curvature that's not actually observed in our data. And in fact, if you were to do this next leading order fit with a free parameter C, you even end up with the wrong sign for that chiral log. So this led us to consider the following two fit models. Either we do a next leading order fit without this chiral log, or we actually just fit the full model as shown here above. Yeah, so that's the result from the first fit model. And now there are three plots. This is the chiral, continuum, and infinite volume extrapolation. The way these plots work is as follows. So there's always the gray data points, which is the original lattice data. And then the red data points are corrected for everything that's not on the x-axis. So in this case, they are corrected for the continuum limit and the infinite volume limit. And they should be described by the blue extrapolation curve. And the blue data point is the physical result that we get out of this procedure. If you look just at the chi-square, I mean, the data are very well described already by this simple fit model. The chiral and continuum extrapolation are fairly mild in this. Finite volume corrections can be sizable if you look at smallish boxes. So that has already been seen in 2019 analysis that was published. The physical result now we get is, I mean, a very good agreement with experiment and also with our value at this most chiral box that sits slightly to the left of it. Now, okay, we can switch to the full next to leading order fit model. And I mean, this doesn't do too much, which is a good thing in some sense. Again, this yields a very good description of the data. The statistical errors, of course, get a bit larger now because you have one additional fit parameter in the game. But if you look at the results from that for the physical value, they actually very well. Now, as I said, this is also not yet final. There's, by the way, one ensemble missing. So this ensemble at 170 MeV pi mass dimension is not in there even yet, because the statistics has not been reached. This has not reached full statistics yet. But for the final analysis, what we'll do is we'll perform also cuts in pi and mass, lattice spacing, and the volume to assign systematic errors to that. Now, one last thing. What I have shown in the previous two slides were results from this two-state fit model. Now you can ask yourself, how does this compare to using just a plain good old summation method? And what you find here is that this gives, again, very compatible results. However, I mean, if you look closely, comparing the results of the plain summation method versus the two-state summation method, you can see that this is a slightly worse fit, actually. That might be a hint that for the summation method, for the plain summation method, you might be even more careful with the choice of your T-submins. Of course, it could also be fluctuation. I mean, this would still be, I guess, acceptable. The reason why I also look at the plane summation method is that actually if you want to go to non-zero Q-square, so if you want to look at the axial form factor, which I'm going to do next, then you cannot really do the two-state fit model with our data yet because you need more parameters. And there's also this problem that the statistical precision for non-zero Q-square data gets worse and worse going to larger Q-square, but you need a method that works everywhere. So this has been very reassuring that you can get away more or less doing the plane summation method, and we will use the plane summation method to deal with the actual form factor data. Okay, so here on this slide, I show the effective form factor for several values of the zinc separation. So these are the different colors on our two most chiral ensembles. So these are very large and fine boxes, as I said, and I mean, you get a pretty good momentum resolution out of them. Now, if you look closely, seems to be this, that the trend for the excited state contamination, so at close to zero, this moves the signal upward, that gets reversed around roughly 0.4 Chef square, so somewhere around here. And then it's actually pointing downwards, so this is why this looks a bit like a fan plot. And yeah, okay, also the signal quality is deteriorating as you increase Q square. But I should mention, okay, we have data available up to 1 Chef square or even slightly more on all the ensembles that enter this analysis. Now the goal for the axial form factor is really to get a parameterization of the physical form factor over a large momentum range as possible. So this is an outline of the analysis strategy that we use for that. Okay, the first step is obviously computing these effective form factors that you feed into your procedure. Then the second step, again, we need to extract the ground state, which is now done by the simpler version of the summation method by a linear fit. This gives you, I mean, discrete data points in Q square on every ensemble. So in order to process this further, you have to then do a parameterization on each ensemble. For this, we use a Z expansion. This polynomial here, in this variable Z, and okay, the zero, the C0, this is just actually again the axial charge. The second one is related to the radius, and then we include one more coefficient. Now then you have then you obtained a parameterization on each ensemble, but you actually want the physical form factor. So the next step is to perform a physical extrapolation of this coefficient Cn. This will finally lead to a parameterization of the physical form factor. And the last step is then to study systematics of all these procedures that lead to that. So, okay, again, to deal with excited states, we have to again convince ourselves that what we do is sound with respect to the choice of this T-set min. What is shown here is the three coefficients Cn on the two most chiral ensembles. The data now is typically, for these coefficients in particular the ones C1 and C2, is much less precise than the axial chart from dedicated analysis. The signal is always lost if you go further to the right. But what you also find is that fluctuations can still be significant below 1 Fermi, especially for C1 and C2. So what we decided for now is to make a rather conservative choice, that is to average always over 3 T-set min values, starting at 0.8 Fermi and then taking the next 3 points. So this is what gives the blue band here. Of course, this increases the error quite a bit. I mean, compared to like picking a single point, like if you would pick a zodiac at this point, you would get a significantly smaller error on that. Okay, then once you've done that, you have to do the physical extrapolation. So this is the chiral extrapolation shown here for C0, C1, and C2. So there's again several choices how we can do that. Either you can use that what was called fit model 1, so the next to leading order fit without the chiral log for all 3 of them. Or you could actually use the full next to leading order fit model for C0 and still use the model 1 for C1 and C2. For, I mean, C1 and C2, there's no hope of, I mean, resolving anything beyond that at the moment. Of course, you have also to take the finite volume and continuum limit. This is also included in the fit model. But here, since the data is much less precise, you simply find that you cannot really resolve any finite size correction. I mean, there might be some effect if you go to very small data, but the error covers everything. So that doesn't do anything. We find again fairly mild continuum limit, but now you actually might need some very mild priors to stabilize that fit for the A square term for this coefficient C1 and C2. Okay, after this extrapolation, you have basically obtained a physical form factor now. This is what is shown in red in this plot. There's also the form factor in this plot for comparison on the most chiral ensemble. So these two bands touch while not quite on top of each other. But I mean, the physical form factor is close to the most chiral ensemble, which I mean is reassuring. So in the difference between the first two plots is okay. The leftmost is the most simple fit model for C0, and then you have the next leading order fit model for C0. That does virtually nothing apart from increasing the error, so that's quite stable. But then, if you, for example, do a cut in the pion mass, this actually has some effect. It moves the band further upwards. So the idea is now to implement further variations of the physical extrapolation to test for systematic effects. So there are many different choices for that. I mean, you can do fit 1 or fit 2 with or without a finite volume term. You can perform cuts in the pion mass, the lattice spacing, and so on. And then we use the archaic information criterion to assign a weight to each of these fits and perform a model average to include finally a systematic error. This is shown on this slide. So the left plot, this is what you obtain for the physical form factor after doing this model average with the full error. So this again increases the error by quite a bit, but it now should cover all these uncertainties in the extrapolation. We also obtain, of course, a result for the axial radius. So this is basically shown here. So these are all the model variations that enter right now. So the statistical and the systematic error both individually of the order of 10%. The result you get for the axial charge from this is smaller than what we had before, but with much larger errors. So they are a factor of 4 larger, because now this does not only is not a dedicated analysis at 0 momentum, but it receives contribution from the entire form factor data in this more complicated procedure. So now I have added our preliminary data point into this plot. It's quite compatible with other recent determinations. Last thing I want to show is a comparison to this experimental data for the form factor. So on the left plot, the axial charge has been divided out. So this is normalized to the value of G8. This is why it's set at 1 to really see the difference in the curvature only. So there's our lattice result. So the dark shaded region is where this actually has support in terms of lattice data. So we do a cut at Q square equals 0.7 chef at the moment. So that is essentially an extrapolation. Then there is various data from fermion electroproduction experiments and the set expansion parametrization of the neutrino deuterium data. So what we see here is, okay, we are compatible with other lattice determinations, but the band we get ends up higher than the experimental result. This effect is slightly more pronounced in our case for data normalized by the axial charges, because we get from this procedure we get a smallish value for it. I should also point out though that there remains some tension in the extrapolation we do. So for right now we might even need a more restrictive Q square cut than we actually did, or I mean we could still include further coefficients in the set expansion. And what we are going to do in the end is we will provide results for this physical coefficients Cn. So including all correlations, so anybody can take them and feed them into whatever procedure they like. Basically, the end of my talk is my summary. So we performed the lattice calculation of the axial form factor on a fairly large set of ensembles that allows us to do all the relevant physical extrapolations. So the result for the axial charge from a dedicated analysis is now in an excellent agreement with the experimental value, and it's also statistically quite precise with all the relevant extrapolations under control. So we're tending to do the same thing for the full form factor. Again, I mean, we use the summation method to tame the excited states, and then we do a physical extrapolation. In this case, yeah, I mean, this model averaging that we did really increased the error. Trying to take into account all the systematics to different choices of, I mean, the fit ansatz or, I mean, cuts you can do in your data. What you find from that, the axial radius and also the curvature of the form factor that we get agrees with other lattice determinations. Finally, we have there's some open ends. So yeah, the production of our ensembles is not yet completed. In particular, we will increase statistics on one of these two most chiral boxes by a factor of 2. That should hopefully further improve the control over chiral and continuum extrapolations. There might also be some work left to do refining the set expansion ansatz we're using and the model averaging. So this is not, I mean, the final result for sure. And finally, I want just to mention that, yeah, again, we have also quark disconnected loop data available on all these ensembles. So in principle, we could also study the quark flavor decomposition in the future. Thank you very much.
Thank you so much, Konstantin. Thank you for leaving ample time for questions and comments. So, are there any questions, comments? Okay, then let's move to Natalie. Sorry, Emily.